Hi, welcome to video lesson number 8. This is on piecewise functions, and just so you know, the next 3 lessons, they don't really connect together at all. It's just 3 kind of standalone lessons, and like I said, this is the longest unit in terms of material, and after that it should be a little bit less material from here on out, or at least from next unit on out. So we're going to understand, interpret, and graph what is called a piecewise function. Starting with the definition, a piecewise function is a function comprised of 2 or more functions defined by 2 or more intervals along the domain. Often the graph is made up of 2 or more different pieces, which may be similar, dissimilar, and/or continuous or discontinuous, each individual part, or the entire piecewise function together. Some things I want to add to this definition, which, by the way, that graphic is an example of a piecewise function. You can see it's made up of 3 different pieces. And we want to go over a few things here. So the first thing is we see closed dots and open dots. A closed dot, so we're going to shade that in. So a closed dot includes the point. And we've been using brackets so far. So if it includes the point, remember, you use square brackets. We haven't used inequality notation very much, but just so you know, if it's a closed dot, it means it includes the point. You could also use a greater than or equal to or a less than or equal to sign. Conversely, an open dot, so we're not going to shade it in, does not include the point. And likewise, we don't use square brackets if it doesn't include the point. We use circular brackets, or if we're using inequalities, a greater than or a less than without the equal to underneath it. So now that we know what a piecewise function is, we're ready to start working with them. And again, ignore the example numbers. I've taken things out, I've changed the order just for the quadmester. So our first example, we're going to graph this, and this is what it's going to look like. You're going to see multiple functions. So what this means is that this is piecewise notation. And this first column, if you will, if you want to think of them as columns, are the functions to use. And this column is the intervals to use. In other words, use those specific domains for those functions. I'm going to color code this. So if we start at the top, f of x equals x squared, and you're only going to graph the function x squared when x is less than 2. So we're going to do that part, and you don't have to color code in your notes. I'm just doing it for your benefit and the people that look at it afterwards. So you're going to start at that point 2. And at 2, if I sub 2 into x squared, 2 squared is 4. And since it's just a less than and not less than or equal to, that means we use an open dot. So 2, 4 is an open dot. Now you can pick all of the numbers, or as many as you want, less than 2. I'm going to stick to whole numbers. So the next whole number less than 2 is 1. And again, we're using the x squared function. 1 squared is 1. Now keep in mind, you only use an open dot at the boundary point, which in this case is 2. Everything else gets closed dots. Go less than 1 is 0. 0 squared is 0. Negative 1 squared is 1. Again, this is x squared. This is just a normal parabola. 2, 4. And if you really wanted to, negative 3, 9, and so on. So there's our first piece. And don't forget x and y. Our next piece, we'll do it in blue. Or I'll do it in blue. So you're going to pick this function, which is linear, 2x plus 3. And you're only going to graph that on the domain greater than or equal to 2. So again, you start at that boundary point at 2. So put 2 into that function. 2 times 2 is 4, plus 3 is 7. 2, 7. And since it's greater than or equal to, it's going to be a closed dot. It's greater than, so pick a number bigger than 2, 3. 2 times 3, 6, plus 3 is 9. So 3, 9 is our next point. And for my graph, that's all that fits on. You kind of have to recognize, going back to grade 9, that's linear. And once you have those 2 points, there you go. So there is our piecewise function. We have a piece for less than 2, and we have a piece for greater than or equal to 2. And if I was to ask you if this is continuous or not, hopefully you're thinking it's not continuous or it's discontinuous because there's a gap in your graph. If you were to hold your pencil on the paper, you'd have to lift it to be able to jump to the next point. Our next example, we're kicking it up a notch. Now we have 3 different pieces over 3 different intervals. It's okay, still manageable. So let's start with x is less than or equal to 0. Start at the boundary, 0. Put 0 into your function, which is going to go into this. 0 plus 1 is 1, therefore your first point is 0 and 1. Then go a little bit less. Again, it makes sense to pick whole numbers. Negative 1 plus 1 is 0. Negative 2 plus 1 is negative 1. We'll do one more. Negative 3 plus 1, negative 2. Again, just looking at it, hopefully you recognize that it's linear, it's a straight line, and this is just going to keep going on forever like that. Perfect. First one done. Our second function, we're going to graph on the domain from 0 to 3 and doesn't include either of those points. So we're going to use open dots on the ends, and we're going to use this function. So start at 0, start at the lowest number. 2 times 0 is 0, plus 1 is 1. So 0, 1. And we already have that point, so you can just make another point right over top of it. Doesn't matter. Now you can pick any number between 0 and 3, but let's stick to whole numbers to make life simple. And again, looking at the function, we know it's linear, so it's not going to do anything crazy in between. Put in a 1. 2 times 1 is 2, plus 1 is 3. So 1, 3. 2. 2 times 2 is 4, plus 1 is 5. 2, 5. And then 3. 2 times 3, 6, plus 1, 7. And again, it's going to have an open dot. Now, if we backtrack a bit, if you're wondering why I didn't put an open dot at the 0, really I could have, and it just would have been an open dot here, but it would have been filled in by the blue dot. So Again, I'm just color coding it, but realistically, if a dot or a point is already filled in, if you put an open dot around a closed dot, it just is a closed dot. But maybe I will go back and actually do that just to make that point. So again, we had it's an open dot there. Our original function had a closed dot. And a closed dot will always fill in an open dot. And there's our second piece filled in. Our third piece of our function, we are going to graph it over this domain. So x is greater than or equal to 3, and we're going to use this function. It is a quadratic. It's x squared, so we know it's going to be a piece of a quadratic. So start at your boundary point, 3. 3 squared is 9. 4 minus 9, negative 5. So 3 and negative 5. And we used a closed dot because it's greater than or equal to. Pick a number bigger than 3. Let's say 4. 4 squared is 16. 4 minus 16 would be negative 12. It's off my graph, but that's okay. We'll just pretend like it's right there. And this is going to be, since it's a negative x squared, it's an upside down parabola, right? So it's going to look like this. And there's our third piece of our function done. Now we want to answer, is it continuous? And remember, if there's any gaps or breaks in your graph, it is not continuous. So looking at this, there is a huge gap between my second and third piece of my function, the red one and the purple one. Therefore, it is not continuous. So we can say discontinuous. And it's always a good idea to justify your response. So not continuous because there is a gap or break across the domain. Hopefully that makes sense. These aren't too bad. And then our next example, we're going to work backwards. And this is, you may recognize that, that's the function from our definition slide. We want to determine the piecewise function of the graph. So we want to determine the piecewise notation for this. So we're going to start with this. F of x equals, big curly bracket. And we got 3 pieces. Working your way left to right, that first piece, it looks quadratic to me, meaning it's going to be an x squared. And that means you kind of have to recall some knowledge from grade 10 and 11 quadratics, coming up with the equation. This one's pretty easy. It has the vertex at 0, 0, and the step pattern. So here's my vertex. And your step pattern over 1, up 1, which just is a normal quadratic. It hasn't been moved up, down, left, right, compressed, or stretched. So this is just x squared. And we use it only for, like, that only exists from here over. And since it's a closed dot, we're going to use less than or equal to. So we're going to pick x squared only for the x's that are less than or equal to 1. And there's our first piece done. Our second piece, that looks quite linear to me. That's just a horizontal line. And if you remember, the equation for any horizontal line is just y equals. Now, we already have the f of x equals part taken care of at the beginning. So we just have to write, this would be y equals 3. So this is just 3. And we have an open dot here and a closed dot here, and that piece only exists from there to there, so between 1 and 2. Does not include 1, so 1 is less than, not equal to, because it's an open dot, x. Now it's a closed dot at 2, less than or equal to 2. And that takes care of our second piece. And finally, our third piece, again, that looks quite linear to me. It only exists from 2 onward and doesn't include 2. And to come up with our equation for a linear graph, we need to come up with our y-intercept and our slope. Slope, that's easy. Over 1, up 1, rise over run. The slope is just 1. So we know it would be y equals 1x, or just x, and then plus whatever the y-intercept. If you work your way backwards, so my next point would be there, my next point would be there, my y-intercept is 0. So it's just x plus 0, or just x. And you use that for all x's bigger than 2, but doesn't include 2 since it's an open dot. So greater than 2. One thing to point out here, these numbers should always match up. So when you have more than one piece, you shouldn't have any big gaps, like 1 jumps to 5, let's say, in the domain. So what I mean by that is, I have a 1 here, this one starts with 1. This one ends with 2, this one starts with 2. If we had a 4th piece or a 5th piece, it would follow that exact same pattern. You should never have, and you should also probably never have less than or equal to's on back-to-back pieces of the function. Just something to keep in mind. So that's working backwards, looking at the graph, coming up with the piecewise. Our last example is a bit of a thinking question. Determine the value or values of k that will make g of x continuous. So you have to kind of, if we're thinking about this, you have to go back to your definition of continuity and what makes something continuous. Well, it means there can't be any gaps. And if there can't be any gaps, that means that at 12, they have to be equal to each other. Otherwise, if they weren't, there would be a gap. Especially since 1 is less than or equal to and 1's greater than, 1 would be a closed dot, 1 would be an open dot. So you need that closed dot to fill in the open dot to make it continuous. So those two pieces have to be equal to each other. So we're going to make a note here. For g of x to be continuous, kx squared has got to equal 4x plus k at x equals 12. If they don't equal each other, there's going to be a gap. So that spells out basically what to do. From there, we just set up an equation. Kx squared has to equal 4x plus k. And since it has to be at x equals 12, you're going to replace x with 12. So k, 12 squared, 4 times 12, plus k. Do the math. 144k equals 48 plus k. And just so you know, I know oftentimes when you get messy numbers, your gut feeling is you did something wrong. A lot of times for these types of questions, you're going to end up with messy numbers. Bring over our k to the other side, becomes minus k. That's going to be 143k equals 48. Divide both sides by 143. K equals 48 over 143. Again, for advanced functions, we are going to leave things as fractions and not as decimals. So there you have it. really kind of your first thinking question for the quadmaster. Not too bad. And if there was 3 pieces, you would do the exact same thing. Set 2 of the pieces equal each other at the boundary, at the numerical value. Your work, there it is, page 51. I'm also assigning the review, so you should be getting a head start on your test review as well. Remember, your test is going to be Friday afternoon, and I will make a little short video coming up after your last lesson just to kind of re-go over with you. This is what my expectations are for the test. This is how you access the test, etc., etc. So for now, consider the review that has been assigned to you here. Consider that concurrent work for you to be working on anytime you have some free time to work on your advanced function work in order to prepare for your test on Friday. Have a good one, and we'll be in touch for the next lesson. Number 8 of 9.